Hello, my name is Sekiyama, Division of Materials Physics, Graduate School of Engineering Science, Osaka University, Japan. In this movie, I would like to talk about my main field, photoemission spectroscopy, as one of the optical processes of electron transition on the basis of the three-step model. This movie is surely longer, but by catching the contents of this movie, you can learn what happens in solids at the electron excitation by high-energy photons and notice that the angle-integrated valence-band photoemission spectra reflect the weighted sum of partial density of states after some approximation. Then the explanation is going to the angle-resolved photoemission spectroscopy called as ARPES, probing the coincident particle or band dispersion of electron in crystalline solid. Please enjoy this movie. Here I introduced photoemission spectroscopy starting from the phenomenon of the photoelectric effect firstly found by Hertz in the late 19th century. Of course, the photoelectric effect are the phenomena that the excited electrons are emitted from the materials into the vacuum after the monochromatic high-energy light is incident. Based on the phenomenon, the concept of light quantum has been introduced by Einstein. The high-energy light means that the photon energy must be higher than the work function of materials. The process of photoemission spectroscopy is like this. At first, highly monochromatic light is coming onto the materials. In this case, material is solid or gas. Then one electron in the material is excited to the unoccupied state. The excited electrons are emitted into vacuum and we detect these photoelectrons by electron spectrometer with scanning the photoelectron kinetic energy directly. This view graph represents the energy diagram of measurement of photoemission spectroscopy. Photoemission process is of course one of the one-photon process following to the film's golden rule, which means that we can use the energy conservation law. When we define the binding energy from the film level located here, EB, we can get the binding energy by measuring the photoelectron kinetic energy, where the energy conservation law is expressed like this. This photograph shows the inside of the photoemission chamber, in this case using the laboratory X-ray source. The incident X-ray is coming from here onto the sample. Then the photoelectrons are emitted from the sample and going to the photoelectron spectrometer, which is not shown here. This view graph shows a real example of the photoemission spectra of gold by using the aluminum X-ray source. The displayed photoelectron kinetic energy range is so wide, including from the 4s core level to 5D valence band. You can recognize the several peaks labeled as 4s, 4p, 4d, 4f, 5p, and 5d states. You can also recognize that 4p, 4d, and 4f core level peaks are split. This is due to the spin-orbit interactions. This is a cross-sectional drawing of the apparatus of the photoelectron spectrometer, of which the photograph is shown here. By using this apparatus, photoelectron spectrometer, we get the photoemission spectra, the relation between the detected photoelectron count versus the photoelectron kinetic energy. Usually, the sample is set to the ground level, and apparatus itself is also on the ground level. That means the chemical potential of the sample, which is equivalent to the film level at zero temperature, is the same as that of the apparatus. The photoelectrons coming into the electrostatic lens set in the front of hemispherical spectrometer with decelerated down to the path energy EP at the front of the entrance of the hemispherical spectrometer. For the deceleration, we apply the voltage in front of the entrance of the hemisphere by using this formula. Then the detected photoelectron travels to the end of the hemisphere, at which only the electrons with the kinetic energy or path energy arrive. Then such photoelectrons are detected. We obtain the spectra by measuring the number of photoelectrons with sweeping the applied voltage V proportional to the target kinetic energy. Although the detailed discussion is omitted, the energy resolution of the detected photoelectrons is expressed as shown this formula, which is proportional to the path energy and slit width in front of the entrance of hemispherical analyzer. In order to measure the photoemission spectra, we need the monochromatic high-energy light. In the last century, the photon energy range is about from 15 to 1.5 kV. The latter energy is near the photon energy of aluminum K-alpha X-ray. Nowadays, the photon energy range becomes wider and wider. The lowest is slightly below 6 electron volt by using laser, which is still higher than the work function of materials in most cases. The highest is of the order of 10 kV in hard X-ray region. When we use such high energy X-ray, we call the photoemission as ARPES, hard X-ray photoemission spectroscopy. Of course, the synchrotron radiation is a very powerful light source for photoemission. In the laboratory, on the other hand, there are several light sources. The conventional laboratory X-ray light source is an X-ray tube supplying the magnesium and/or aluminum K-alpha lines. For the low-energy excitations, the conventional source is a helium discharge lamp. On the other hand, now the other new laboratory sources are developed. For instance, the continuous laser with a photon energy less than 10 electron volt and xenon discharge lamp, giving the 8.4 electron volt photons. The high-energy X-ray light source using the chromium K-alpha line is also developed for the hard X-ray photoemission called as ARPES in laboratory, which is one of the most promising new technique. From this slide, I would like to explain the theory of photoemission process, mainly using the three-step model. It is known that the so-called inverse lead process is theoretically accurate for describing the photoemission process. Recently, one-step theory, including the inverse lead process, has been developed, and one-step theory calculations are much improved. However, the one-step theory is rather difficult for beginners. So, I use a phenomenological three-step model, but its practical validity to describe the photoemission process of the crystalline solid at low temperature for probing the ground state electronic structure has been confirmed. Advantage in the three-step model is that situation becomes clear in the process. In other words, we can easily imagine what happened in solid in the photoemission process when we consider this model. In the three-step model, we divide the photoemission process into the three steps. Before going to the first step, I call step 0, the monochromatic photons are coming into the solid. Then the first step, step 1, is the creation of a photoelectron, in other words, photoexcitation. The second step, step 2, is the travel of the excited photoelectron to the sample surface without inelastic scattering. In the three-step model, inelastic scattering is not treated. Therefore, the background due to the inelastic scattering is out of focus in this model. The last step, the step 3, is emission of photoelectron into vacuum. In the one-step theory, these processes are treated simultaneously. Considering these steps, we can express the photoemission spectrum as a function of photoelectric kinetic energy, and incident photon energy is the product of the function in each step, namely the function p in step 1 times function t in step 2 times the function d in step 3. It should be noted that the electronic structure is mostly reflected in the term of p in step 1 because the initial state electronic structure is included only in step 1, excitation of an electron. Before going to the detailed discussion, I comment the notation of the state I or F. In the previous lecture, state I or and F has been used as a notation of the state of both electron system and photon field represented by the direct product. On the other hand, the discussion of the electron spectroscopy, including photoemission spectroscopy, state I and F are often used as a system of electron system alone, not including the photon field, since the main issue on how to probe the electronic structure by electron spectroscopy. In these lectures, following to the ordinary notation, from now, state I and F are employed to the state of the electron system. The notation is like this. Here, I wrote the photon momentum as Q. This is because K is used for the electron wave number in solids to be surveyed. As I discuss later, Q is quite smaller than K in most cases. It also should be noted that the notation A.P is often seen in the textbook, where the state indicates solely the electron system. However, it is rather unreasonable after the vector potential is quantized. If we quantize the light, namely the vector potential is quantized, we need to treat simultaneously both electron system and photon field. But when we measure the photoemission, the interesting point is how to probe the electronic structure. Therefore, I or F are often used for representing the electronic structure or states of the electron system solely. Okay? So let me start from step 1, creation of photoelectron, in other words, photoexcitation. According to the Fermi's golden rule, the transition probability WFI, which represents the transition probability from the initial to final state in photoemission process, is expressed as this formula. Here, N represents the number of electrons of the system. The state I stands for the state of the large N electron system before excitation, and F stands for the photoemission final state of N electron system, including one excited photoelectron. Then the total electron energy of the final state is expressed by using this formula, namely that is the sum of the photoelectron kinetic energy in vacuum, the work function, and the total electron energy of the residual n-1 electron system. Here I use two important assumptions, which are employed for almost all discussion of the photoemission spectroscopy. One is that only one photon process takes place. This is natural. No one expects that the multi-photon process is predominant over the one-photon process. The other is that the created photoelectron does not interact with the residual n-1 electron in the final state. This is called as sudden approximation, which is justified by the fact that the photoelectron energy is much higher than that of the residual n-1 electrons. In this case, interaction between the photoelectron and the other electron could be negligible, since the off-diagonal terms is relatively much smaller than the energy difference between the diagonal parts, namely the diagonal energies of the photoelectron and other electrons. Then, the photoemission process can be divided into the core-level photoemission process, which probes the valence-band electronic state through the interaction with the created core hole. The chemical shift is one of the results of such interaction. And valence-band photoemission process, which directly probes the electronic structure reflecting the density of states. The difference between the core-level and valence-band photoemission process is whether the core hole is created in the final state or not. For easy understanding, I first discuss the process for non-interacting electron system in the photoemission process from the next slide. This is a schematic energy diagram of a non-interacting electron systems representing the difference between the XAS process and photoemission process, where the photoelectron final state phi f has much higher energy compared with the excited electron in the XAS process. Of course, the character or orbital symmetry of photoelectron is determined by the same selection rule. Here, I defined non-interacting electron systems as a system in which the Coulomb interaction between electrons are negligible or can be treated within a mean field approximation. Then the electronic state of the residual n-1 electron does not change before and after the photoexcitation process. Therefore, these formulas are satisfied for the photoemission process. Since now we consider non-interacting electron system, the photoemission process becomes a one-electron problem. These two formulas are satisfied only when the non-interacting system is considered. The initial state energy can be divided into the residual n-1 electron energy and energy level of the one electron state phi I to be excited. This energy level is relative to the film level for solids. For non-interacting electron system, the residual n-1 electron energy is the same between the initial and final state. Then the transition probability giving the part of the spectral function is expressed like this, which is obtained by putting this relation into this formula of the term of P transition probability. This term becomes finite only when the photoelectron kinetic energy has this relation. On the other hand, the binding energy is defined as this formula. Here this one stands for the one electron energy level of the state phi I. When we compare these two formulas concerning the photoelectron kinetic energy and binding energy, we notice that electron binding energy is a minus of one electron energy level to be excited, epsilon phi I. This relation is called as Koopmans theorem. Owing to this theorem, we can understand that peak binding energy EB directly reflects one electron energy level epsilon phi I. When we find the peak, we can notice that the peak corresponds to the one of the energy level. Then I go to the next step, step 2, which is related to the surface sensitivity of the photoelectron spectroscopy of solids. Term of T represents the probability of the photoelectron motion to the surface without inelastic scattering. In other words, without energy loss, as a function of the absorption coefficient alpha of the incident light and the photoelectron mean free path lambda as a function of kinetic energy in solid. Usually, the mean free path of the incident light is expressed by the inverse of the absorption coefficient alpha is much longer than the photoelectron mean free path except for the extreme conditions such as the total reflection condition. Therefore, usually the term of T is expressed like this, proportional to the photoelectron mean free path lambda, which is from a few to 100 angstrom as shown in this figure. In this sense, the photoemission spectroscopy is more or less surface sensitive measurement. The photoelectron mean free path lambda takes minimum as 3 to 5 angstrom, like in the kinetic energy range from 15 to 100 electron volt. This energy range corresponds to the conventional helium discharge lamp and vacuum ultraviolet VUV synchrotron radiation. This situation is happy for surface science because the minimum lambda of 3 to 5 angstrom correspond to the thickness of the topmost surface layer. This means that the surface electronic states can be obtained by the VUV photoemission. This is rather unhappy for the scientists who want to probe the bulk or buried layer electronic structure of solid where the surface states are often highly deviated from the bulk ones. The mean free path becomes longer gradually as the photoelectron kinetic energy increases. Around the kinetic energy of 1 kV, the mean free path is longer than the 10 angstrom. Therefore, the bulk, a spatially deeper region from the surface, can be probed by the Valence-band photoemission at the soft X-ray excitation because the kinetic energy of the photoelectron near the film level is comparable to the excitation photon energy. Further going to the 5 to 10 kV range called as a Hawk space region, the mean free path becomes order of the several tens angstrom, around 50 angstrom, very bulk sensitive. On the other hand, the kinetic energy becomes lower from the minimum range as below 10 electron volt corresponding to the xenon discharge lamp and UV laser. The mean free path sometimes, but not always, becomes longer again. In this sense, this kinetic energy corresponds to the observed kinetic energy in vacuum plus a few to several electron volt because this axis represents the photoelectron kinetic energy in solids, which cannot be accurately evaluated. This kind of the kinetic energy dependence of the photoelectron mean free path in solids is caused by the fact that the inelastic scattering of photoelectron in solids caused by the valence plasmon excitation and interband transition, of which the energy scale is of 15 to 30 electron volt. Here, we should remember that interaction easily takes place between the system with a comparable energy scale. Then the scattered photoelectrons are detected as a secondary energy-dependent background. Here I show the photoenergy dependence of the photoemission spectra reflecting the surface sensitivity based on the real experimental example valence-band photoemission spectra of ytterbium-boron 12. Here you do not need to know the physical property of this compound but focus on the spectral line shape near the film level. These peaks are due to the ytterbium 2+4F contribution. In addition to two sharp peak structure, you can recognize the broad peak, two-peak structure. This is from the surface ytterbium 2+4F contributions. These contributions are strongly suppressed when we measure the same valence-band photoemission spectra at the soft X-ray excitation at 700 electron volt. This is the spectra of same compound, ytterbium-boron 12. This is from the surface ytterbium 2+4F contribution. These contributions are suppressed. However, the surface contributions are still seen at the photon energy of 700 electron volt with non-negligible weight. The surface contributions are almost completely suppressed at the excitation energy of 8 kV as shown in this figure, where the broad structure seems to vanish. These are realistic examples of surface or bulk sensitivity of photoemission as a function of the excitation photon energy as well as the kinetic energy. Surface sensitivity of the photoemission can also be controlled by changing the emission polar angle of photoelectron with the same photon energy when we measure the material with very flat surface with kinetic energy of several hundred electron volt like this. This view graph shows an example of the strontium 3D equilevel photoemission spectra of layered strontium leucinate as a function of the emission polar angle theta of 0 and theta of 60 degrees. At the normal emission with a polar angle theta of 0 degree, we see the shoulder structure at just the higher binding energy side of the sharp peaks. This shoulder structure becomes peak in the spectrum of the polar angle theta of 60 degrees, which is more surface sensitive condition with grazing condition. By analyzing the data by the least square fitting, the contribution from the bulk topmost surface strontium oxide layer S1 and second strontium oxide layer S2 has been obtained like this. The clear surface equilevel shift have been detected from the emission angle dependence of the shallow core level photoemission spectra as shown in this figure. Then I would like to explain the step 3, third step, the photoelectron emission into vacuum. Here it is assumed that photoelectron in solid can be treated as nearly free electron because the kinetic energy is much higher than that of the residual bound electron in a solid. Of course, the photoelectron kinetic energy in vacuum Ek is positive, which is the case for Z larger than 0 in the schematic figure shown here. Inside the solid, for the minus Z less than 0, we can set the photoelectron kinetic energy as Ek star as Ek plus V0 in the solid. For this formula, it is assumed that V0 is independent on position in the solid. This approximation is justified by the fact that the V0 is much smaller than the photoelectron kinetic energy and hence the effect of the periodic potential in the crystal can be negligible. Usually the V0 is called as inner potential, which can be evaluated by the photon energy dependence of the angle resolved photoemission spectroscopy as shown later. Of course, this potential is 0 in vacuum. One important thing is that the derivative of the potential by x or y along the sample surface direction is 0. This means that the photoelectron does not feel the force in the x and y direction in the surface when the photoelectron is emitted into vacuum. Therefore, the photoelectron momentum is conserved along the direction to the sample surface at the emission process. Namely, a small kf parallel is equal to the large k parallel, which can be detected. Then the relation of the photoelectron wave number between the vacuum and solid is expressed like this. In order to observe the photoelectron, the large K perpendicular must be positive, and Kf is obtained by this formula. Furthermore, angle theta prime has a maximum angle less than 90 degrees. Then the probability of the photoelectron emission into vacuum, the term of D is expressed by this formula, which can be analytically integrated like this. Then finally, we obtain the term of D as this form. This function has no peak structure but changes gently on Ek, observed photoelectron kinetic energy, like this. Especially when Ek is above V0 in a potential of the order of 10 electron volt, this function depends very gently on the kinetic energy Ek. Therefore, usually we do not need to worry about the bad effect of this term in the observed photoemission spectra. Here I revisit to the photoexcitation step 1, and explain what we can get concerning the probed electronic system, also based on the real example of the photoemission spectra. In this formula, Ek and work function phi are the quantity in step 3, the emission into vacuum. On the other hand, the excited photoelectron energy level in solid can be defined as epsilon phi f equivalent to the Ek plus phi. The state phi f is one of the eigenstate of the electron Hamiltonian. By using the photoelectron energy level epsilon phi f, the term of P is rewritten as this formula, like this. In order to obtain the practical valence-band photoemission spectral function for non-interacting electron system, we need to consider the fact that all valence electrons are severally, independently, in another word, excited. And further, we should consider the sum over all initial and final one electron states. Therefore, the term of P proportional to the spectral function is expressed by this formula. This is a fundamental photoemission spectral function for the non-interacting electron systems. Then I proceed to further simplify the spectral function by using the few reasonable assumptions. When the one electron transition term, E dot P term, is independent of the initial and final one electron wave function phi I and phi f, and hence the E dot P term can be regarded as a constant, the terms of P is simplified as this formula. This is not so realistic but effective when the valence band is made of only one orbital or band formed by one orbital. Further, when the final state photoelectron energy defined as Ek plus work function phi is higher than the several tens electron volt, such photoelectrons are nearly equivalent to free electron. The density of state of the free electron is proportional to the square root of the kinetic energy in solids, which means that the density of state of the final state depends gently on the kinetic energy. Therefore, we can regard that as a constant within the realistic scanned energy range. When we define energy omega as Ek plus phi minus photon energy correspond to the minus of Eb, binding energy, the term of P becomes to be proportional to this one, equivalent to the density of states. Namely, the obtained valence-band photoemission spectra are basically proportional to the density of states. Here I show the real example of the experimental valence-band photoemission spectra of simple metals. At first, the valence-band photoemission spectra of aluminum, in which there are no d band in the valence band. The line shape is somehow similar to what we expect density of state of the free electron-like itinerant sp band. You can also see that the so-called sudden drop in the intensity at the film level. This is called as film cut-off or film edge, which indicates that this material is metallic. It should be noted that film cut-off is not seen in the spectra of semiconductor or insulators due to the presence of the band gap. In this sense, whether the film cut-off is seen or not is an important qualitative test for that the surveyed material is metallic or insulating. When there is a relatively narrow and localized d band in the valence band of simple metals, the obtained spectral line shape becomes qualitatively different for that of aluminum. Such examples are shown in the middle figure, the valence-band photoemission spectra of simple metals copper and silver. In the spectrum of copper, a strong spectral weight is seen in the binding energy from 2 to 5 electron volt. This is due to the localized 3D band contribution, where free electron-like 4sp band contribution is seen like this one. In the case of silver, on the other hand, the localized 4D band contribution is seen in the spectrum from 4 to 8 electron volt, where the 5sp band contribution is observed like this. These spectra can be well explained by the schematically drawn density of state as shown in this figure. Okay? Here, I explain the photoionization cross-section, which is practically important for the photoemission measurement. In the previous slide, in order to obtain the equivalency of the spectral function to the density of state, we have assumed that the transition probability E.P term is a constant independent of the initial and final state one electron wave function phi I and phi f. In reality, however, the E.P term depends on phi I and phi f and polarization of the incident light. To obtain this term, we need to calculate this integral. Here, for simplicity, we consider within the dipole transition. In other words, we apply the long wavelength approximation. Then the exponential term can be approximated as 1. And further, we consider the photoemission process of a single atom or ion with hydrogen-like atomic orbitals. Then the initial state 1 electron wave function is represented by the product of the radial function with the quantum number n and l and the spherical harmonics with the orbital and magnetic quantum numbers l and m. For the final state, the photoelectron is nearly free electron-like. For such a state, it is known that the wave function can be expressed by using the partial wave expansion with the formulation is shown here. RKF L' stands for the radial wave function of the continuum state with the energy of a kf square over 2m. M stands for the electron mass. The photoelectron is no longer in the bound state, so the wave number kf is a good quantum number instead of the principal quantum number n in the final state. This part represents the phase shift of each partial wave, which is not so important here. Since the photoexcitation process is one of the optical processes, and we discuss within the dipole transition, the selection rule is shown like this, which means that only the L plus minus 1 wave component contribute to the final state photoelectron wave function. Further, we assume that L plus 1 transition is predominant, which is in reality in most cases when the photoelectron kinetic energy is well higher. Here the photon energy h nu appears since the energy difference between the initial and final states must be the same as the excitation photon energy owing to the energy conservation law. Then this formula is proportional to this one. This formula is so long, but gives us the important information. At first, this part represents a polarization dependence, which can be analytically calculated since E dot R hat is proportional to the one-order spherical harmonics. This part gives the photoelectron angular distribution with respect to the light polarization. And this part gives the photoionization cross-section related to the angle integrated spectral intensity. Also, by taking the L-1 transition into account and neglecting the interference effect between the outgoing L+1 and L-1 photoelectron wave, the cross-section for each atomic orbital labeled as sigma NL is expressed as this formula within the dipole transitions. Here, R L+1 prime stand for the integral of the product of the radial function of the initial and final state. The calculated photoionization cross-section for several atomic orbitals are shown as a function of the photon energy like this. It should be noted that these curves are more realistic and practical, where the non-dipole effects are also taken into account. We obtained practical angle integrated valence-band photoemission spectra as the sum of the partial density of state for orbital L, weighted by the photoionization cross-section. In the next slide, I show the realistic example of the valence-band photoemission spectra of ternary compounds. This figure represents a valence-band angle-integrated photoemission spectra of ternary compounds cerium palladium arsenic and cerium palladium antimony by measuring the different photon energy 875 electron volt and 114 electron volt. Since the cerium 4f electrons are so localized in these compounds, it is expected that the band structure calculation for the Ransam palladium X will explain the photoemission spectra with non-4f component. It is also known that the cerium 4f cross-section is relatively negligible at these photon energies 114 and 875 electron volt compared with the non-4f orbital cross-sections. The two spectra of the same compounds are mutually similar, but the relative peak intensity, for instance a spectral weight around 1.5 electron volt, is different each other. According to the photon energy dependence of the photoionization cross-section, at 114 electron volt, The theoretically calculated photoemission spectrum is represented by this formula, the sum of the partial density of state weighted by the cross sections. This is displayed by the solid black line quantitatively explains the experimental photoemission spectra. At the photon energy of 875 electron volt, the palladium 4D cross section is much stronger than the other ones. Therefore, the spectra are expected to be the line shape of the palladium 4D density of states. Actually, the experimental photoemission spectra at this photon energy are well explained by the palladium 4D density of states alone. From these examples, we can notice that it is very worthwhile to compare the valence-band photoemission spectra with the result of the band structure calculations. From this slide, I talk about angle-resolved photoemission spectroscopy, widely called as ARPES, which is powerful to probe the detailed electronic structure of valence band as well as the quasi-particle structure in the vicinity of the film level. When the probed material is single crystalline with very flat surface in atomic level, ARPES is available to probe electron momentum in addition to the energy in the initial state. The momentum is conserved at the photoexcitation process, step 1, including the incident photon momentum and the crystal momentum in other words, reciprocal vector G. At the process of the emission of photoelectron into vacuum, the momentum is conserved along the parallel direction to the sample surface. So, Kf parallel is obtained as a function of photoelectron kinetic energy in vacuum Ek and the emission polar angle theta, both of which are observable quantities from the experiment. Then we get the electron momentum along the surface direction Ki parallel by this formula. Also for the perpendicular direction to the sample surface, the momentum along this direction is obtained when the nearly free electron approximation is available, which is the case for the situation that the photoelectron kinetic energy is enough high. Ki perpendicular is represented by this formula. Here, the plus direction of the photon momentum Q is taken along the downstream direction opposite to the photoelectron propagation direction, and hence this sign is plus. Then, when E.P term representing the transition probability can be regarded as a constant for simplicity, ARPES spectral function is expressed as this formula. Here the index L stands for the band. Compared with the simplified angle integrated photoemission spectral function, two Kronecker delta concerning the momentum conservation are multiplied in the ARPES spectral function. Usually, ARPES spectral function is expressed as a function of momentum in the initial state Ki and electron energy omega instead of h nu, Ek, and theta, with holding the relation shown here. Using the Dirac identity, the delta function is expressed as an imaginary part of this complex function where eta stands for the tiny positive number, in other words, infinitesimal. This complex function is equivalent to one particle retarded Green's function for non-interacting systems. Namely, the ARPES spectral function is equivalent to the imaginary part of the one particle Green's function, which has an important role in the theoretical field of strongly correlated electron systems. Here, I introduce a practical formula to obtain Ki parallel in the unit of Ångström inverse from the photoelectron kinetic energy Ek in the unit of electron volt as shown here. Roughly speaking, the half of the square root of Ek in electron volt is the value of the momentum, a wave number in the unit of the Ångström inverse. It should be noted that photon momentum Q can be negligible for the excitation photon energy less than 100 electron volt, since the value of Q is at most 0.05 Ångström inverse, which is much smaller than Ki, electron momentum. Here I show that the momentum is surely conserved at the photoexcitation process. At first, we should remember that both initial and final states are eigenstate of the electron Hamiltonian. When the potential is spatially periodic, which is the case for crystalline solid, the initial state wave function with the momentum Ki is expressed by using the Bloch function as displayed here. Here, large R stands for the lattice vectors represented by the linear combination of the primitive lattice vectors. On the other hand, the function UKI can also be expressed as this formula. Here the vector G stands for the reciprocal vector. Therefore, the initial state wave function with the momentum Ki is also expressed by this formula. For the final state, the free electron-like photoelectron wave function is also the eigenstate of the electron Hamiltonian. Therefore, the photoelectron wave function with momentum Kf in the solid is expressed by this formula. Then, the transition probability E dot P term is calculated as this formula from above G's formula. Here the reciprocal vector G in the initial state wave function is replaced by G2'. The gradient of the exponential function is easily obtained. Therefore, this formula is also rewritten as this formulation. We notice that the integral of the exponential function over the space becomes 0 when the exponential is like a plane wave. In order to get a non-zero value of the transition probability, this part in the exponential function must be 0. Therefore, the momentum Kf in the final state is the same as the sum of vector Ki, Q, G2' and minus G. When we redefine the vector G as G2' minus G', we get the formula of the momentum conservation with the crystal and photon momenta at the photoexcitation process. By this way, we can guarantee photoelectron momentum is conserved before and after the photoexcitation step 1. Okay? In this slide, I show the real example of ARPES spectra. The probed samples are cerium, nickel-2, germanium-2, showing the heavy fermion superconductivity at low temperature, and its reference material, lanthanum, nickel-2, germanium-2, showing the normal metallic behavior. The intensity maps as a function of binding energy and momentum along X gamma direction for both compounds are shown here. For lanthanum nickel-2 germanium-2, a dispersion similar to that of the free electron band crossing the film level is seen with the band bottom at the X point. For the cerium nickel-2 germanium-2, on the other hand, there is a similar dispersion to that of lanthanum nickel-2 germanium-2, but the difference is seen in the vicinity of the film level with so-called the kink structure. Kink means a sudden change in the slope of the curve. This one. This behavior is also confirmed by the energy distribution curve called as EDC's ARPES spectra, shown in the left side. For cerium nickel to germanium 2, the spectral weight remained even after crossing the film level vector Kf for lanthanum nickel to germanium 2, suggesting that the film wave vector is shifted to the direction away from the X point, and slope defined by the dE/dk becomes very small in the vicinity of the film level. This means that rather flat band is formed along this direction, and thus the heavy quasi-particles are formed for cerium nickel to germanium 2, which is consistent with the macroscopic thermodynamic measurement of specific heat. We can also evaluate the effective mass m star of this band. For lanthanum nickel to germanium 2, the estimated m star is 2.1 MeV, where MeV stands for the free electron mass. For cerium nickel to germanium 2, m star is evaluated as at least 22 times heavier than the free electron mass, showing the signature of the formation of the heavy fermi. From the detailed and high-resolution ARPES measurement, the important property of the conduction electron can be revealed as shown in this figure. Finally, I would like to show that the film surface can also be detected by the photon energy dependent ARPES, which is now called as three-dimensional ARPES. These data show the ARPES spectra along the different directions in the brilliant zone in a reciprocal space for cerium ruthenium to germanium 2. These ARPES spectra have been obtained by the changing polar angle theta, whereas these data have been measured by changing the excitation photon energy. Then we focus on the spectral weight in the vicinity of the film level. The film wave number Kf is the wave number at the film level, and hence the spectral weight is strong at the Kf. Therefore, the momentum distribution of the photoelectron intensity at the film level principally represents the cross-sectional film surface like this one. For cerium ruthenium germanium 2, the result of the momentum distribution of the photoelectron intensity at the film level is shown here, where the white dot represents Kf film wave vectors. Then we detect the cross-sectional film surface as displayed here. So this view graph shows the data from the photon energy dependent ARPES spectra, and this view graph shows the result of the two-dimensional cross-sectional film surface by measuring by the changing angle with a fixed photon energy. To summarize, by using ARPES, band or quasi-particle dispersion and the film surface sheet can be detected.